Hey, the star of the show today is going to be the ratio test. And we're going to have some nitty gritty lawyer like rules here, but let's give a little intuition first. If I had a series and I started to write out the terms of the sequence of that series, I can think of these as having a relationship as a future term and a previous term. For example, a sub 3 is a future term compared to the previous term. But a sub 3 is a previous term compared to that future term. And if you think about it, your intuition about whether a series is convergent or divergent rests upon trends you see as you compare future terms to previous terms. But of course, you're always skeptical because you know your intuition is not always going to be correct. Well, this intuition is put into specific language here. It's a little bit intimidating at first, but it's simply saying this. Let's do the limit as n approaches infinity of a future term compared to a previous term. A sub n plus 1 means we're one term further than the previous term. And what this is saying is, if that ratio is less than 1, then our series is convergent. If that ratio is greater than 1, then our series is divergent. And just like the nth term divergence test, be careful, you don't always have a conclusion. In this case, equals 1 is a no conclusion. Well, to put this intuition, I'll use divergence as an example, but we could do the same thing with that. You could kind of put that into the intuition we were talking about above. If this ratio is greater than 1, we conclude divergence. And the reason is, this is a fancy way of saying the future terms are getting larger relative to the previous terms. Pretty easy intuition. The rule itself looks a little bit clunky, and the actual work you have to do is going to be quite detailed. We'll go through one problem example. Here's our example. And it doesn't look like it fits into any of the famous families of series. And I'm going to spill the beans right away and tell you that we're going to eventually conclude divergence. But what I want you to focus on is the detailed work that we have to do to get this done. If I'm going to use the ratio test, that's the first thing I put down on paper. Limit as n approaches infinity of a future term compared to or divided by a previous term. A future term is the current term plus 1n further, plus 1n further. So n plus 1 further, n plus 1 further. So just be very careful because you'd be tempted sometimes to write down n squared plus 1, but that's something different. So future term divided by previous term, and the absolute value is there. Because you could be doing this where your ratio is heading in the negative direction or the positive direction. You could have a series with negative terms, positive terms. Don't really worry about that if that's not making sense to you. Just know that you're going to have that in there because a series can be divergent by heading towards big old positive numbers or big old negative numbers. Well, this should be on your paper to show the AP grader that you're using the ratio test. And you will get partial credit or not partial credit based upon you writing this. So I know you're naturally resistant to writing limit or absolute value, so be careful. When I take this, I think, man, there's no way I can do that limit. But I can do this beautiful eyeball adjustment. Dividing by a fraction is like multiplying by its reciprocal. In fact, if you would prefer to go straight to this, that's okay, as long as you're writing everything out. So you could skip that first step because you know you're going to go to this step. Well, you still have that limit to do, and you might remember us doing limits like that earlier in the year, or you may have blocked it out. From this eyeball adjustment, I'll go forward and do one more eyeball adjustment. And here's what I said. This term and this term, they're really easy to compare to each other in a limit. So I'm just going to rearrange so they're comparing to each other. And these two are going to be easy to compare in a limit. Now here's why I did that. If I think about this, that's kind of like this old algebra thing. If you had x to the 7th over x to the 6th, you know by algebra rules, that's x to the first power. So this can be reduced to be 4 to the first power. There it is. And limit as n approaches infinity of 4 is just going to be a stubborn old 4. This piece right here, you probably don't take the time to do what I'm about to do, but if I felt like multiplying out the denominator, it would be n squared plus 2n plus 1. The limit as n approaches infinity of that is the limit as n approaches infinity of that, and what we have is a battle of the big dogs. The strongest exponent in the numerator is a 2. The strongest exponent in the denominator is a 2, which means we kind of get to ignore that. And as n approaches infinity, the numerator compared to the denominator, that's a tie, and so that would be 1 if I'm doing this as a limit problem. Well, the purpose of this eyeball adjustment going from here to here was to make these comparisons a little bit easier for my brain to digest. So now that becomes a 4, that becomes a 1, and limit as n approaches infinity of 4 times 1 is just a plain old 4. Okay, so if I have that 4, now I go back to these rules, or the intuition in my brain. Because the result of my limit was greater than 1, and 4 is greater than 1, I say divergent by the ratio test. Just beware, this is going to take plenty of practice for you on the homework, because think of how many goopy limits we can have, and you need a little practice because you're probably not going to be able to get all those limits perfectly the first time you see them, if that first time is on an AP test or a unit test. That's the ratio test. I hope you enjoyed this.